So in this class, we're going to learn how to write the functions, how to define functions in Python. So suppose a program you are currently writing contains several lists where each list must be printed in the same format. With these elements separated one per line with numbered lines where this code is needed in several parts of the program. It would be highly useful if there was a way to give this code a name, like a mini program within your main program file. So that mini program name become a piece of code that a program can call whenever it is needed. This mini program are actually what we call functions. Naturally, in Python, the most common recognizable functions are built in, so some of which are the most frequent ones you have been using so far, including but not limited to like print or input int, etc. And these built-in functions are written by the creators of Python that can be used without needing to provide the function definition to your program. When we call a function use it, we pass it the information it needs to carry out its work by placing the information inside this parentheses. Those items we passed into a function, these arguments in technical language, used the data represented by each item to complete its task. Some built-in functions are designed to change the type of an object from one type class to another when it is possible to do. Python will report back a value error otherwise if it cannot be converted. Similar for objects with structure, the functions like list, dictionary, and tuple can convert or create sequences of various forms. The timing and placement of function call also matters. For example, the flow of this program when it is executed jumps to the piece of code of the print function when that is called each item, then returning to the program when it is done. Every time this print is called, the items in each call are displayed in the output on separate lines where each items of the sequence separated by a single space. And the last item at the end is a new line character to move the program to the beginning of the next line, ready for the next print call. We have been using the print function in its simplest form. If you noticed in an earlier unit, we used a keyword argument file to send the output of print to a different file object. Similarly, we have been using the default arguments for the print keyword arguments, where like they separate separate is equal to like empty or space in here, and equals to the new line character when we do not specify them. If you like, we can specify our own string to use as separator, as well as the one to be used at the end after the last item by passing them as special keyword arguments to print. The first argument in here, the first print in here uses the empty string as a separator so that the base and ball are conjunct and ends with a space rather than a new line character. The second print ends with both a period and an explicit new line. So in general, many functions have optional keyword arguments you can specify when you call it. Recall from the master program that the random module was imported to generating the two random numbers for the operand of each question. We use it to pick a pseudo-random integer from 0 to 9. Technically, those values are never truly random, but they seem to be so. In general, when we use a function from a module, we must use dot notation to specify the module name first and followed by the name of the function that comes from it. Of course, for mathematical functions other than max and min, we can use a few other available to us as built-ins, such as the sum function, which can accept a sequence of numbers and calculate their sum. and this absolute value function will return a numerical expression and return its argument to be positive. You can also import the math module for a variety of other functions, such as the trigonometric function and some exponential function, etc. When the function is not already part of the Python, we can create our own to either be fruitful, so it will return value, or avoid, which will not return anything. So after we specify a distinct name for it and write the block of code to carry out its task, it functions by its name and pass in any arguments it may need within the parentheses. And the arguments passed in can be values, variables, generally any expression it will require as input. The function will extract the value of the arguments to carry out its task. Most people just call them functions when the meaning is clearly understood. Using functions makes programs easier to understand by breaking the words into pieces. So a second advantage is that small pieces are easier to write and test than the larger ones. So frequently we proceed by writing and checking a number of small functions, using this to build other functions and so on, until eventually we can accomplish the main work of our program just by making a handful of function calls. And the third advantage is that once a function is written, it can be reused. So it is true in two senses. So the first one is a function can be reused within a program. For example, once it is defined, it can be called at more than one piece in our word. And significantly, if we write the user-defined function today for use in one program, there is nothing to stop us from using it in another program. And moreover, we can share useful functions with other programmers. Actually, we have already done that, like its len, split, and lower, and other functions. All these functions we reused from someone else's previous work. To start, consider writing a function that can be called without any argument needed. So it should appear reminiscent to a control statement, except for the header line, where we use this define statement, short for the define, to create a function object with a specific function name you decided to correspond to the block of code below it. And whatever names that the function is what you must specify for the call to it. So like the message parenthesis would output the user the function is called. Like variable names, function names in Python share the same rule of naming convention. Like particular for functions, it is good practice to name it based on what it will do. If it is primarily used to do something, name it with a verb to describe what the performed action is. For example, like convert, rejoin, shuffle, etc. Or if it is primarily used to return a value, name it with a noun, like average, length, word list. The name should convey that what kind of data the function yield for your program to use. Like built-in functions that require arguments, it is also possible to pass in arguments to your own defined function as well. We can write functions that takes in as many items as we like. What happens when we pass several items is simple as long as you know how to call a function that accepts arguments. Like each argument of data, whether it is a string, number, list, or any other object, gets assigned to a parameter that is used in the function block. So the assignment of objects in a function call are made by position. The first name in the definition is assigned to the first item passed in the call, and the second name will be assigned to the second item, and so on. Either way of how a function is defined with or without arguments to use parameters, Whenever a function is defined to yield a value, we use a return statement to accomplish that. And wherever a return is encountered inside a function, the function stops work immediately and returns the specified result. So when the function is called, the result essentially replaces the function call. But when a return statement is not specified at all in a function, none is the default return value for that function. If you recall from a previous unit, we cleaned up each line of text from this Hamlet text before processing the histograms of words. However, it does make the overall program rather hard to understand, such as doing that cleanup right in the middle of the program task. A much better way would be like the following. Don't try to run it now. It does not yet work. But however, here we have called a function named as cleanup to do all the works of the text cleanup, certainly making the program neater and easier to follow. Recall that statements are executed in order from top to bottom in the program, beginning with the first statement of the program until it finds a control statement, going through each until it terminated at the end of the program. Function definitions get executed like other statements, but the effect of define is to create a function object. Statements inside the function do not get executed until the function is called. If the function call appears before the function definition, Python will report a name error that the function is not defined. Thus, the function has to be defined first before the function can be called in the remainder of the program. The new part is the definition of cleanup at the top of the program. Notice the letter S in parentheses on the first line of the function definition, a single parameter, and when the function is called, a string of the text will be passed for it to clean. The name S will refer to this string, and if you notice, we wrote cleaned up in the program, and in this case, the line in the string passed to the function, and S will refer it. Actually, as the first step in executing this function call, the interpreter just does a simple assignment that is S is assigned to line. So the name of the variable passes as a function argument has nothing to do with the name of the parameter. When the function begins to work, the S refers to the string to be cleaned, and the body of the function, other than the last line of the return statement, contains nothing new since it is mostly the same code we used in our previous version of the program to build up a clean line of text. And at the end of the function, like clean text refers to the resulting string that the function should return as its answer. So function definition do not alter the flow of execution of the program, but must be defined first before they are called. Suppose we play a betting game based on coin flips. Starting with an initial bet, if it's heads, we earn $1, and tails, we lose $1. We keep playing this game until we double our initial bet or lose it at all. On average, how many flips will this game work? So instead of calling this function over and over again, we should consider a series of experiments to call the function for us. We can call a function within another function, and we will give this new function a list of different amounts of money to use for initial bets, and how many games to try for each starting amount. And then it will carry out all the experiments and report back on the result. In the short program, notice the following. The one-game function is defined first before it is called in the experiment definition. And the first item passed to the experiments is the list, and the second is the integer. These are matched when the game given in the first line of the function definition. It means that when we make the function call, the interpreter starts by executing two assignments, the initial and the repetition, and then it continues with the statement in the function body. What if we wanted to know a root RO of the cubic polynomial, where the parameters a, b, c, and d are real numbers, and we want to know for any given numbers the root such that the p is equal to 0. And naturally, it is best to use the formula if you know and understand it. But instead of relying on the mathematical knowledge, we can take an approach that is much more general. We can use it to solve not only this problem, but a wide range of others, including many in each. No one has the mathematical knowledge to give a formulatic answer right away. For example, we study the root of polynomial function, and the approach we will use to begin is just trial and error. Since it is so straightforward, we will automatically it later on. Rather than giving guesses all the time, we will just keep track of the limits of the range of possibilities and let each new guess to be midpoint of the range. For example, if we know the number is between -5 and +5, we will give the program automatically guess it is 0. We use a for statement to make a series of 2,000 guesses. Each guess is the midpoint of the current range of the possibilities as low limit and high limit. We use result to return the value of the polynomial with this guessed value, and if the result is above 0, our guess was too high. So it becomes the upper limit to use it for the next guess. And if it is below 0, then our guess is too low and it becomes the lower limit. Either way, each new guess causes the range we are exploring to be cut in half. So in this way, we very quickly home in on the answer we want. Running the code, we get this answer. I promise. We get the answer. Okay. Now we will improve the program one step at a time. First, move the this trial and error code to a function called goal-seek. And rather than have numbers like 100 low limit, 100 high limit, and 0 built into our functions, we passed them in as arguments. And rather than always making these 2,000 guesses and hoping that narrows down the range sufficiently, let's make as many guesses as necessary to achieve a specified level of accuracy. The goal-seek function is modified so that it takes a fourth argument, which specifies the largest error we will willing to accept. For each new guesses, we checked to see how far off the result is from what we want, and continues as so long as this error is more than the limit we've set. We have already seen default arguments in the print function, but this is the first time we are creating our own function that provides one. In the function header, we specify a default value of 0.01 for max error, and if we leave out this argument when we call this goal-seek, this default value will be used. So the first of these two test calls in our program, we don't specify the maximum error. The default value of 0.01 is used, and we get the answer. And in the second call, we asked for a smaller error and get our more accurate answer. The goal-seek function is currently useful only for automating trial and error exploration of this one particular function. Likely, Python treats the names of function just the same as names referring to integer, list, or any other kind of objects. Remember, when we write this definition, this Python function, the Python assigned the name example to the function object with a given code. So if we wrote this triple assigned an example to the triple, and this new name actually refers to the same object as the original. We can write this print function to get 30 as output. The upshot is that we can easily generalize store set so that it works with any function we specify. We just need to pass in the function name. Now that the goal set can work with any function, and we can specify for any polynomial function we like. And our goal set function is now very serviceable, but we would like to calculate the root of any coefficient. And we specify for a cubic polynomial, not just the one in poly and poly 2. Each of these root calculations will require a function along the lines of those two functions to be passed to the goal set. And clearly, we don't want to have to create all those functions manually. Once again, it's lucky for us to let the Python treats function objects and names it as same as objects and names for anything else. If we can write functions that return lists and integers as values, we can just as easily write functions that return functions. And the new function makePoly defines and return functions along the line of our early poly functions, but using any numbers we specify for the coefficient a, b, c, and d. We show how it can be used to create the two specific functions we defined it manually earlier, but of course now we can define any numbers of similar functions with ease. When we write our programs, we literally reuse names, run this program for a moment and study it line by line. We use the name year in the main part of the program to refer to the integer, and if you run the program, you will see the year still has this meaning in that last line. Of course, it is no surprise, but how can we account for the fact that it is true even through year is reassigned it to refer to the integer in the call to the next year, and that is assigned it to 10 other integers in the call to defeat. The answer is that the program actually uses three completely separate names. One is the name year used in the main program to refer to 1832, and another is named year used only within the next year function. It takes on a value whenever a call is made to next year, and within the function it is reassigned to the next higher number. And the third name is also called year, and it exists only within the decade function. Within the function, it is assigned to a series of integers by the for statement. If you're not sure why we could use the same name 3 times throughout the program, let's specify the context with a different example unrelated to the programming. Several people may share the name like John and Emily, although they have nothing else to do with one another. Certainly, if one John and Emily has a birthday and the other are unaffected. Likewise, what we do with a name that is a local to a function, those defined within, has no effect on an identical name in another function, such it applies it only within that local scope. So this local also has no effect on the global name, one that is defined outside any function. Still, we must be careful when the arguments are passed to the function call are changed, so that is for each parameter the function gets a references to the object, even when the object is assigned to a variable. And for example, if a list is passed to a function as an argument, the parameter is an alias to that list, meaning that a particular object, even if it goes by a global name, can be changed every time the function is called on it when the parameter is directly altered. So think about the code we stated below, line by line for a moment, and it appears similarly to what the parameter of the user-defined function when it accepts arguments does when a variable within a value is passed as an argument for that function call. Aliasing is when an object that is assigned to the variable's value is indirectly assigned to another. So if an object has more than one references, so that it goes by more than one variable's name. This behavior is tricky and prone to errors, so it is generally safer to avoid altering those parameters in a function when objects can be modified. Such as lists and dictionaries, it is not a troublesome for certain unchanging objects like strings. The list variable a has two references, meaning it has two alias. So those variable names point to the same object. One of these aliases is variable a for the references between the list and variable a, and another alias is variable b. The other references is between the list and variable b. And if you are unsure if something points to the same objects, use the if keyword in Python to check as a condition. So significantly, anything that happens to the object when using the name variable b does not change the fact that it is the same object that the variable a is assigned to. To return the original object, we must write the function to return a different value without directly modifying the original parameters. Consider the doubling of the numbers in the list, and the printed result of the original list reveals that the original list has not been modified after the function call, and that doubled list is the returned value of the function when it is called. Occasionally, we do want a function to make a change in a global name. In this case, we must identify the name as global using a global statement, run the program, and study it line by line. After the call to the next year, the name year in the main program still refers to 1832, despite the reassignment within this function. After the call to make it be next year, however, the name year in the main program refers to 1863. And the simple rule is if a global name is to be reassigned with a function, it must be identified as global. So it is not necessary to identify a name as global if it will be used but not assigned. Recursion is technical when defining a function that it can refer to itself. So a function that calls itself is said to be recursive. When creating recursive function, it must consider these four key concepts: an argument that is used for recursing downwards, a condition to test when the argument is whatever the lowest possible value is allowed for it. This is called the base case, and a return value for this base case that does not use the function itself. A recursive call to the function with a different argument other than the current value. As this program demonstrates, recursion can always be used in place of loops, such as listing the directories within other directory. Try running this program for yourself to list all items in the parent directory of the program code. The full power of the lister function takes a little while to think it. Take a moment to consider what happens if we call the function this way instead of calling it on the parent directory of the program file. The function would list out all items contained at the top level of the directory structure. Some of these would themselves to be folders, so the lister would automatically to be called again to produce a listing of the items they contain. But some of these would also be directories, meaning that the lister would be called yet again one level deeper. Continuing in this way, the single function called lister will produce a listing of every file in every folder on the entire hard drive. In fact, a lister is very much like the Unix command list R. Before we produce anything like the large amount of output, let's input the way it's displayed. Let us pass to the lister function a string to print before each file name. And when each new call one level deeper, we make the strings a little longer with 4 spaces to present each descending level of directory compared to the directory that is called upon. The last line is where the main work begins, with a call to lister on the parent directory of the program parent directory. And Unix, it would be like double period / double period. We call on the directory with an empty string to begin listing that directory at the topmost level.